Hello again, everybody, and welcome to May. We really are getting on toward the end. This is our next to last week of class. For the past couple of weeks, we've been talking about conic sections, different shapes that you could cut out of a cone or describe in terms of distance. The first big conic section we talked about last week, that was a circle. And a circle, of course, was all the points in a plane that were the same distance from a fixed point. And we learned all about equations of circles last week and how those worked. Another conic section is a parabola, and we learned a lot about parabolas when we studied quadratic equations last fall. We're not really going to talk about them more now, other than to remember that, yeah, they are one of the conic sections. There was also a conic section called a hyperbola, which the shape of the cooling tower that you're looking at in the picture would illustrate. Hyperbola we're really going to focus in on next week, but the important thing about it was that they always had two different branches. And that brings us to the ellipse, which is the conic section we're going to focus on this week. In the picture, you can see one of the biggest applications of the ellipse, which is that the orbit of pretty much anything follows an elliptical shape. Here you can see an illustration of the moon revolving around the Earth, and that does make an ellipse. The Earth revolving around the sun is also an ellipse, and all of the bodies in the heavens basically follow an elliptical shape when they move. An ellipse, of course, looks something like this. If I asked you what it looks like, most people say it's like an egg shape or an oval, and that is basically true. The technical definition of an ellipse is kind of like the definition for circle. What it says here is that an ellipse is all the points in a plane where the sum of the distances to two fixed points is constant. Remember, for a circle, you had the distance to one point was always the same. Here it's the sum, you add up the distances to two fixed points, and that ends up being constant. All the points in a plane where the sum of the distances to two fixed points is constant. So the idea of that is that you start with 2 points. And I've got a series of pictures here that shows you what happens. If you can picture like taking a string and attaching them to nails that are at those 2 points, and then taking a pencil and moving it out as far as those strings will stretch. If you trace around and you always keep the pencil stretched out as far as it'll go, that's going to keep the sum of the distances to those points the same. And what will happen as you keep going all the way around is that you're going to end up with an ellipse. You start with those 2 fixed points, you keep the sum of the distances to those points the same, and if you look at all of the places together that have that, you have an ellipse. The most important thing about an ellipse are those 2 points that you measure from. And we call each of those points a focus. The two together we call foci. That's a very typical Latin plural where you take something that ends in us and it turns into an I. So yeah, the focus is one of those points. The two of them together are the two foci. I mentioned earlier that one of the biggest applications of an ellipse is orbits, and while I find the pictures here very strange and that the Earth is shown bigger than the Sun, they are giving you the idea of orbiting in an elliptical pattern. Here's a whole bunch of things that have ellipse shapes. You might not think about like the Oval Office at the White House. That certainly is elliptical. So are a lot of different brands or trademarks or symbols for things. When I did a quick Google search, I got a laugh out of the fact that one of the things that came up was elliptical foods, and you can see some different food shapes, all of which are ellipses. There is a really important property of ellipses that's used in a variety of ways. It says that anything at all that goes through one focus will reflect off the ellipse and go straight to the other focus. That's kind of an odd property, and ellipses are the only time that's ever true. Here's a couple of things that show you how that property works. Back at the start of the pandemic, a lot of you were hoping to go to New York City, and if you'd done that trip, one of the quick stops you'd probably have made would be at Grand Central Station, biggest train station in the world, which is in New York City. It's a very big, very busy train station, but it happens that a large part of that station is shaped like an ellipse, and it has what's called a whispering gallery. You can actually stand at one of the foci of the ellipse, which they have marked there, and your friend can be standing hundreds of feet away at the other focus of the ellipse, and if you whisper, nobody's going to hear you except that your voice is going to reflect off the ceiling and go straight over to where your friend is. So above all of the noise of the station, you can talk to each other with nobody else hearing you. There's a lot of other places that have whispering galleries too. You can find one at the US Capitol and another at the Museum of Science and Industry in Chicago. And the whole idea is that in spite of all that noise, because of how the reflections on ellipses work, if one person's at one focus and the other one's at the other focus, you can hear each other. The other picture you see here is of what's called an elliptical pool table. When I was in college, they had an elliptical pool table in the basement of the Union at UNI. The way it works is there's just one pocket on the pool table, and it happens to be at one of the foci of the ellipse. If you just shoot the ball randomly, chances are it's not going to go anywhere near that pocket. In order to get the ball in the pocket, what you've got to do is aim so that it goes through the other focus on the other side, and then what's going to happen is it'll bounce off the side of the table and go straight into that pocket. I played that a couple of times when I was at college, and it was honestly kind of a fun game and very different from normal pool. I've actually linked a little video that shows you how that works. It's just a short thing where the guy is showing you how to play elliptical pool and how you can actually always win. So far we've talked about the two foci, one focus and the other focus, which are those points that you measure from when you do the distances that go into an ellipse. Here's some other terms that come up when we're talking about ellipses. Two of those are the terms major axis and minor axis. What the major axis and minor axis are is they're kind of like the diameters of an ellipse. The major axis is the diameter of the fattest possible part. It goes all the way across the longest possible length in an ellipse. The minor axis is the shortest possible distance from one side of the ellipse to the other. Vertex means the ends of the major axis. Co-vertex means the ends of the minor axis. I will tell you honestly, those terms I'm not going to be asking you about. Major and minor, though, do come up. And what's actually almost more important are the terms semi-major and semi-minor axis. Semi just means half. And so when I talk about the semi-major axis, that just means halfway across the fat part. Basically, it's from the center to the vertex. So like the radius of the widest part of that ellipse. Here's the standard equation for an ellipse, and you can kind of imagine when you get to the quiz, you're going to have to either come up with some equations or match equations to shapes, kind of like you did with circles last week. And it's actually, while it may look complicated, it's kind of an easy equation to use. There are, however, a couple of small things that some of you goofed up with circles that you want to make sure you don't goof up when you're working with ellipses. So what this equation says is x minus h squared over a squared plus y minus k squared over b squared equals 1. And it tells you, first of all, that h and k, those are the points from the center. Now, just like when you did circles, the equation has minuses in it. So it's always the opposite of what the numbers for those points are. If I had the point 3, 4, it would say x minus 3 and y minus 4 on top of those fractions. So hk is the center. A and B are the distances from the center to the edges. What those literally are the semi-major and semi-minor axes. They're how far you go across and how far you go up and down to get from the middle of the ellipse to the outside. Notice those are squared, just like r was squared when you did a circle. That's always squared when you have an ellipse. So x minus h squared over a squared plus y minus k squared over b squared equals 1. So here's an example. It says x minus 3 squared over 49 plus y minus 4 squared over 13 equals 1. Now there's a couple of things that I can tell right off looking at this ellipse. I can tell the center has to be at the point 3, 4. And just look at the opposites of those parentheses on top. The x value has to be 3, the y value has to be 4. So 3, 4 is going to be the center. And yeah, if you look at this picture, that's pretty much where the center is. The other two things that this tells me is that the distance going from the center across to the edge of the ellipse is going to be 7. It's the square root of 49, which would be 7. Going up and down, it doesn't come out to be a whole number. What it's going to be is the square root of 13. That's like about 3.5. But it just means to get from the center up to the very top or down to the bottom of the ellipse, I go the square root of 13. The one other thing that can be useful when you're working with ellipses is this little formula. It says you can find the distance from the center to the foci using this formula. The first part says c squared equals a squared minus b squared. The other one says c squared equals b squared minus a squared. It's kind of like the Pythagorean theorem, but with a minus in it instead of a plus. Now that's saying if I look at the numbers that are here, what I would have to do to figure out how far it is from the center to the focus is take 49 minus 13, subtract those numbers on the bottom of the fraction, and then do the square root. If you do that, I would have the square root of 36, which is 6. And if you actually do measure 6 units across from the point 3, 4, well, 3 plus 6 is 9, and you notice they've got the point 94 marked as one of the foci. And if you do 3 minus 6, you get negative 3. That's what's marked over on the other side of the ellipse. So yeah, to get the distance from the center to the foci, you subtract those numbers on the bottom of the fraction. That's actually the least important of the rules we're going to talk about with ellipses, but it is the one other thing you can learn from that equation. So here is a real typical question, the sort of thing you might see when you get to your quiz. I've got a picture, and you can see that the center of this ellipse is at the point 2, 0. The top and bottom are at 2, 2 and 2, negative 2, and the left and right are at 1, 0 and 3, 0. And our question asks, what's the equation of this ellipse? Well, remember our formula said x minus h squared over a squared plus y minus k squared over b squared equals 1. Think about that for just a second and see if you can figure out what this one's going to be. And on the top of the fraction, I've got x minus 2 squared, and then y squared. I could have put y minus 0 squared if I wanted to, that'd be okay. On the bottom, since I go across 1, that's why there's 1, or 1 squared, which is under the x part. And since I go up and down 2, I did 2 squared, or 4, under the y's. So x minus 2 squared over 1 plus y squared, or y minus 0 squared over 4 equals 1. It always says equals 1 at the end of the equation for an ellipse. Here's another one. Again, take a minute and see if you can figure out what we would have for this one. This time the center's at the origin. So on top I just got x squared and y squared. Again, you could put minus 0 with each of those, but there's really no reason to. We go across 7 and up and down 2. This is marked in 2's. And that's why my equation is x squared over 49 plus y squared over 4 equals 1. And here's a third one. Again, they kind of all work the same way. You've got to figure out where's the center, how far do you go across, how far do you go up and down, and then put it together in an equation. And here we would have x minus 2 squared over 16 plus y plus 1 squared over 9 equals 1. Again, on the top, you always have the opposite sign of what the point was. So since the center is 2, negative 1, that's why I've got x minus 2 and y plus 1. And again, when you do those numbers on the bottom, it's always half the distance across squared. So like to get from the middle to the edge, I go across 4. That's why I've got 4 squared or 16 on the bottom. And again, let's look at this one. And this time it's going to end up being x plus 3 squared over 4 plus y minus 4 squared over 25 equals 1. Again, always a plus sign in the middle of those two fractions, always a 1 at the end. Now when you get to your quiz this week, I'm not going to have you actually graph anything because that's pretty much impossible to do on a computer quiz. However, I do want you to be able to look at an equation like this, figure out where's the center, how far would you go across, how far are you going to go up and down. So see if you can think about those things as we go through this. And the sort of questions I might ask you on the quiz would be, where's the center? And here it will be the point 5, negative 1. From there, you would go 4 to the right and 4 to the left. You'd go 1 up and 1 down. And again, those are the things, the center, the semi-major, and the semi-minor axis, those would be the things I might ask you about this. If you put them together, you'd get a graph like this. Again, just the nature of how the class is working this spring, I'm not going to literally ask you to graph things, but hopefully you can kind of see how that's going together to make the ellipse that we've got here. Again, see if you can think about everything that would go into the graph on this one. So hopefully you can figure out that the center is going to be at the origin, 0, 0. Now when you look at those numbers on the fractions, it is important that if the bigger number is under x, it's going to be short and fat. If the bigger number is under y, you're going to have a tall, skinny ellipse, and that's what this one actually is. We're going to go 2 to left and right, and 4 up and down, because those are the square roots of the numbers on the bottom. And so here's the basic shape we'd get from this ellipse. Again, center at 0, 0, go across 2 from that center, go up and down 4. So the last thing you might be asked deals with how far it is from the center to the foci. And again, this really is the least important of those. It becomes important like if you were going on into engineering and were building those whispering galleries or elliptical pool tables. It's honestly in everyday life the least important of the facts though. How far is it from the center to the foci? Well, the big thing here is remember that formula that was kind of like Pythagorean theorem, but with subtracting. So all you do is you just subtract the two numbers on the bottom of the fraction, 4 minus 1, and then you do the square root. So it is going to be the square root of 3, which happens to be about 1.73. Sometimes people ask me, which way do you subtract? It's always big minus small, so that's why it's 4 minus 1. And if you tried to do it the other way, you'd get like a complex number answer. But yeah, here it's the square root of 3. And so here's another one where we want you to figure out how far is it from the center to the foci. And again, the big thing with an ellipse is you got to subtract those numbers on the bottom. It's the opposite of what that sign in the middle says. So 16 minus 9 is 7, and that's why my answer is going to be the square root of 7. And that is pretty much it for this week. Next week, we will be taking a look at hyperbolas and then wrapping things up for good. So we are almost done with everything. I do wish you well. You do have some problems you can use to practice that. And of course, you got a quiz about ellipses you'll be working on this week. So have a good week, and we will see ya.